Hello, we're talking about Kepler's laws here, and we're going to be essentially trying to distinguish. He's got between these three laws here. So our learning goal is to use Kepler's three laws to predict the orbital motion of celestial bodies, right? And specifically, we're going to look at the period, frequency, and radius, and kind of see how those get determined, right? Now, the way that his first law is set up is that it's a nice little observation that the guy made is that all planets move in an ellipse rather than a circle. Previously, folks thought planets moved in a circle, and so Mr. Kepler decided that it was the ellipse that would be more appropriate shape to determine the path of a planet. And so if you take a look at this diagram here, our ellipse is here, okay? And that's the path of the planet there. Okay, just one quick thing is the definition of an ellipse is, let's say I focus on this point here. It is the same, or if these are the two focal points, okay? The sun is one of them, and this is another focal point. There's actually nothing there, just some empty place in space, but it's the focal point. Okay. If I take the sum of these two distances, these two blue lines that I just made, it should be equal to the sum of these two blue lines, right? Oh no, screwed that up. That was not correct. It's these two blue lines here, this one and that one. And it should be equal to the sum of these two blue lines, okay? That's the definition of ellipse, okay? Anyway, so that's just a quick discussion of the shape of the ellipse. Kepler's second law says that a straight line joining a planet and the sun, so that would be this line here, sweeps out equal areas in equal intervals of time. So here's a planet. As it moves around like this, some time passes. We'll call that time 1, okay? And that sweeps out a certain area here, okay? Then let's take another point, the same planet, same sun, but later on in its orbit. We'll sweep out another time. And this area here is going to get sort of defined in a way, right? Straight line sweeps out this area. Well, if this time and this time are the same, then these two areas are the same. That's one of Kepler's rules that he discovered as well, okay? Now, Kepler's third law says that the cube of the average radius of a planet's orbit is proportional to the square of its period. So that's the radius cubed is proportional to the period squared. That's what this is. So the radius cubed is proportional to the period squared, okay? Which is basically this. All right. And now the is proportional symbol can be replaced with equals C. Okay. Why? Well, because proportionality just means that as one sort of increases, the other one increases as well. So you've got some sort of ratio or proportion that is always the same. So basically, the ratio of 3 cubed over t squared is always the same, and it's just some number, right? And so you can rewrite it like this, okay? Right here, right? And if you look closely at that, if I solve for c, right, then I can pass the t over, and that's basically what I was just saying right here. This is the ratio is always the same. It's always equal to that, okay? And this C is a property of the sun, or the the central object that everybody rotates around. Let me erase some of this stuff here. Okay, so basically what I want to talk about is, let's say we've got a sun here. I'll explain this rule. We've got a planet here, right? And it rotates around in a circular or somewhat elliptical path. The average radius, let's say that this is a circle. The average radius is always the same, right? Okay, because it's always the same. Let's say we've got another planet, a green planet out here, right? I don't have green anymore. It's blue. Let's say it's blue, all right? The blue planet might have this as its orbit, right? And basically, we've got an average radius. Sometimes it's pretty close, sometimes it's really far. But if you were to sort of make multiple radii and take the average of all of those, that's going to be your average radius, or this r in this formula. Okay? And the period is just the time it takes to rotate around. Okay? And this little cs is a number that corresponds to the sun. All right. All right. So let me go through an example question here. Right. Use the Earth's average radius. Sorry, average orbit, orbital radius and period. I think I was supposed to have the word radius in here. And period to find the sun's constant of proportionality. So that's this. Okay. And we've got the radius here. We've got the period here. And so we're going to basically just find the constant of proportionality for the sun, which is this value. Okay. And there we have it. It's equal to the average radius cubed divided by the period squared. Okay. So I went ahead and I plugged all these numbers in, and it looks like we've got a constant of proportionality, or C, for the sun of 3.4 times 10 to the 21. Hopefully I typed those numbers into the calculator correctly. I've been making a lot of mistakes on that lately. Okay, so this is the average radius. Okay, now an asteroid has a period around the sun of 50 years. Find its average orbital radius. So since both the Earth and the asteroid rotate around the sun, basically what we have is that they both can use this constant of proportionality. So the constant of proportionality is the same for both the Earth and the asteroid and Saturn and Jupiter, and anything that travels around our sun uses this constant of proportionality. Okay? So now questions might ask you to find certain radii or periods of different other objects. And so you basically just use this formula here, right? We know that its period is 50 years. We know that it's traveling around the sun, so it uses 3.4 times 10 to the 21. And we can now find its average radius, find the average orbital radius of this asteroid. And so you basically just do a little bit of algebra and you solve for it over here. Okay. Now notice this needs to be placed into seconds in order for you to get everything calculated. Okay.